Welcome to our Engineers Newsletter Live program. Today, we'll provide designers with some considerations and options for upgrading existing chilled water systems. I'm Jeannie Harshaw from Trane's System Engineering Department, and I'll be your host today. Before we get started, let's quickly cover some housekeeping. This course is approved by the U.S. Green Building Council for 1.5 GBCI continuing education hours toward the LEED Credential Maintenance Program. Upon successful completion of this course, LEED professionals may submit their hours to Green Building Certification Institute at gbci.org. Today's program is also registered with AIA's continuing education system and qualifies for the Health, Safety, and Welfare and Sustainable Design credit. So make sure you provide your member number to your local host before leaving today's session. In several states, certificates of completion can also be applied to your engineer's continuing education requirements. So please check your state's rules to see if this applies to you. Now today, we'll provide specific strategies for chiller upgrades, optimization, or replacement. You'll learn how to apply various design strategies to determine the opportunities they offer existing systems. We'll walk through how to apply the use of variable flow in existing systems, and finally, how to identify and apply control strategies to optimize and reduce system energy use and lower energy costs. Today, we'll discuss the drivers for considering chilled water plant upgrades and types of chiller replacements. We'll cover upgrading existing chillers and opportunities for repurposing chillers. We'll expand the discussion and include reusing components of the chilled water system and identify areas where control upgrades would be beneficial. Finally, we'll wrap it up with a discussion of condenser side opportunities. To cover this information today, we're delighted to introduce Bonnie Spalding, a Trane Service Products Manager who will provide some insight on upgrade options for chillers and what designers should consider. Mick Schwedler, Applications Engineering Manager and immediate past chair of 90.1, authored an article on today's topic. Today, he'll take us quite a bit deeper into design parameters and system configuration. Susanna Hansen, an Applications Engineer, will provide an overview and later discuss control options. Now, the discussion for upgrading a chilled water plant begins for a number of reasons. One is that the system's not working well anymore, or the building's purpose may have changed. Energy management reduced the lights and the building construction was improved, or it may be that the building is simply no longer operating efficiently. A U.S. Department of Energy funded study concluded that commissioning is indeed cost-effective for both new and existing buildings over a range of facility types and sizes. The median energy cost savings were 15%, with payback periods much less than 1 year. New buildings can justify commissioning as well, with energy and non-energy impacts combining for an extremely short payback period. Widespread commissioning of existing commercial buildings could save the nation over $18 billion a year in energy costs alone. So Susanna, there's a lot of opportunity when it comes to upgrading. Could you get us started with today's discussion?
Sure. System not working comes in several flavors. Often the equipment may be approaching the end of its useful life. Limping along with old equipment is tiring to building staff and to operating budgets, not to mention the impact it has on building occupants. Another reason the system might not be working is that it is out of capacity. But for many, reason to upgrade the chilled water system is energy bills are simply too high. Utilities change their rates frequently, and it just might be time to change a building's energy use behavior to minimize the impact of the higher rates. An obvious reason for a chilled water plant upgrade is when the building is repurposed. As the vagaries of the economy shift our business needs, existing buildings are being asked to be more flexible. Spaces once used for office work might now be doing light manufacturing or vice versa. New tenants are attracted to well-operating, comfortable spaces. Production capacity shifting. That can mean addition or reduction of process cooling loads. So whether it's a subtle or an abrupt change in building loads or a lit fuse on necessary equipment replacements, Whatever the reason for upgrading, it doesn't make sense to start the project with the chilled water system. Take a hard look at the rest of the building beforehand. Reduce loads. It's no surprise to anyone that lighting and envelope improvements save a bunch of money. Lighting retrofits save energy twice when spaces are being cooled, but their improved efficiency may add to space heating requirements. On the flip side, envelope improvements save especially on heating. When you take a look at your spaces, how many under-desk heaters or fans do you see? An energy audit can identify those items and also tell you a lot about what the deficiencies are in your building. So let's talk about reducing loads in a meaningful way. Simultaneous heating and cooling is often one reason why a building blows its HVAC budget. When spaces are comfortable, this energy waste can be overlooked. One hidden simultaneous heating and cooling happens because of stuck or broken heating valves. They put additional heat into a space that might now need cooling and might even convert a system from one mode to the other. Leaking return air dampers can add a lot to the cooling or heating coil loads. One study by Lawrence Berkeley National Labs showed leaking return air dampers adding 46% to the required cooling energy and 6% to heating energy. Control issues are common. Look for rogue zones that do not respond to control or have vastly different needs than other areas on the same system. It could be that the design was inadequate, the sensors are inaccurate, or the set points have been modified. Rogue zones need to be identified and addressed because they'll almost surely waste energy. If a dynamic control is looking at zones for making decisions and one or more rogue zones are never happy, the entire control may not work. The automation system may have provisions for removing rogue zones from polling or voting algorithms that reset static pressure, ventilation, or temperature set points. Next, overrides. Did someone forget to adjust the schedule and forget to put it back? We've all been in meetings where it was too hot or too cold. Maybe it was a sluggish control or a system that couldn't compensate for the load fast enough. So someone went over to the controller on the wall and made a massive change, or the building operator might have overridden a schedule or a set point in the system. The event's now over. Did the room settings get restored? Overrides create rogue zones. Is there an office with its set point a lot lower than the others? You might not ever get to use your reset strategies if the president's office is always set to 60 degrees. Remove these overrides whenever it's possible and prudent. There are almost surely a host of energy conservation measures that can be initiated. Most of these tasks are grouped together and collectively referred to as retro or recommissioning. Now for me, recommissioning also asks and answers these two fundamental questions. Does the system work well as it was designed or intended to operate, or was the system as designed fundamentally flawed from the outset? These flaws might only be obvious in some instances or in some modes of operation. Perhaps humidity control is a challenge, but only at part load. This can be exacerbated if the system is oversized, or if too much chilled water reset is being used. What situations trigger the problem? You may have a short amount of time to go from unoccupied to occupied mode. If the system is too small or the changeover not anticipated, you may think the system can't handle the loads. Think of a church that's mostly unoccupied all week. Can you pull the environment back to the occupied state fast enough? Prudent use of controls can help. Features like optimal start can identify the right amount of time needed to change modes. Is the controller acting too slowly or hunting? Now, you can't fix a chilled water system until you know what the problem is. It may be that the chilled water system performance is not the cause, but the symptom of a badly operating building. The data is out there, usually too much data. By seeking out data, converting it to information, and then acting on it, you can identify and correct building energy waste. Let's look at two examples of data turned into actionable information about how a building is operating. Here's an example of an airside control that is available but not activated. Now the bold red line on this chart is the average VAV box position. We can see that on Monday morning, the box is opened at 5 a.m. to bring the zones into the occupied state. But by 9 a.m., no box is more than 50% open, signifying that the duct static pressure was not reduced to save fan energy. In this case, reducing the fan static pressure set point could have saved a significant amount of fan energy. The extra fan energy adds cooling load to the system through fan and motor inefficiency, which amplifies the energy saving opportunity. Here's a zone in a system scheduled on for every hour of the day. For some reason, this zone is not satisfied. The VAV box is starved. In this example, it is unable to meet the load with the maximum flow setting. It was rarely able to achieve the cooling set point of 62 degrees. Because the VAV box is wide open most of the time, it defeats the duct static pressure optimization algorithm. Potential reasons for this problem include an unattainable zone set point, it could be an override, a failed actuator, a poor sensor location, or a duct balance or design issue. Identify the reason this zone is unsatisfied and correct it. If it's a frequently recurring issue unrelated to any of these factors, for example, in the case of a loading dock where the doors are open some of the time, the zone can be removed from the duct static pressure optimization or other dynamic controls such as supply air temperature reset. Is system size truly the issue? Now, in a few minutes, we'll look at some of the ways we can expand or contract chilled water system size to increase our ability to cool spaces. Now that you've identified the problems with the building and its controllability and reduce loads where possible, we can move on to upgrades within the chilled water system. Let's start with the chiller. Two options to consider are replacing or retrofitting the chiller. In some cases, the chiller may be older and ready for replacement. We'll discuss the importance of sizing the new chiller properly and also examine two similarly priced chillers. In either case, we need to make sure that the replacement chiller complies with ASHRAE 90.1 requirements, on which the local codes are often set. So when the time comes to replace the chiller, there are a lot of options to consider. One is, should my high efficiency come from copper and compressor, or from a variable speed drive, or both? Are incentives available? Most people want to have some measure of conservatism. The good news is that since this is an existing plant, a lot about the building operation is already known. There are fewer unknowns than in a new building. The question to ask is, do I want extra tons or extra lift capability? In existing buildings, the chilled and condenser water pipes are usually unchanged. If I think I may want to expand the system later, buying an extra chiller might not work because the tons may not fit in the pipe. While Mick is going to go into this topic later, I bring it up now because planning for the future does affect the chiller selection. But in any case, when I replace the chiller, I have to bring it up to today's energy code. Your handouts have the 90.1 2010 requirements for chillers. We just did a program on 90.1, so I'll save some time and skip over those requirements, which are included in the next 4 slides in your handouts. When considering a chiller replacement, first figure out what size chiller is needed. Don't just replace a chiller with the same capacity new chiller. If the load is reduced enough, you may be able to switch to a different style of chiller to meet budget or space constraints. Now, I talked about building changes that reduce the loads. What about system expansion? There may be times when the load has increased. In these cases, one of the challenges may be reusing the existing electrical system. Efficiency can help you here. Let's say you have a 400-ton chiller that's 25 years old and the nameplate says 272 kW. That's about a 0.68 kW per ton. If the capacity required is now 550 tons, a new chiller at 0.5 kW per ton full load will need about the same electrical input. That could easily bring the job back into budget. But if you want to have a variable frequency drive, a similarly priced chiller would require a larger electrical service. Or for a given electrical service, you might back solve for the largest chiller available to maximize chiller capacity with the existing service. Besides electrical service size, to reduce energy use and cost, a higher efficiency chiller can reduce demand and consumption charges, whether it's constant or variable speed. And when considering which chiller technology is the right fit, the discussion turns to the circumstances that benefit constant or variable speed technology. Here's a quick refresher from a past ENL program on BFDs. The load a chiller satisfies is a function of the flow rate and the difference in evaporator entering and leaving temperatures. The lift a compressor must develop is proportional to the refrigerant differential pressure between the evaporator and condenser. In turn, that pressure difference is proportional to the condenser water delta T. In this case, at design conditions, the load is 500 tons and the lift is 58 degrees. Load and lift are related to total compressor work, ultimately corresponding to the amount of potential energy savings. Here's a graphic showing the compressor work rectangle to illustrate the relationship. The width of the rectangle represents the mass flow of the refrigerant through the compressor and chiller cooling capacity. The height of the rectangle represents compressor head, or the lift required of the compressor. So referring to the previous example, the load is 500 tons and the lift is 58 degrees. Mass flow, or tons, is defined by the building. For a given mass flow, the speed of the compressor can only be reduced if the lift is reduced. Lift is reduced, 1, by lowering the condensing temperature by delivering colder condenser water than design, and 2, by increasing the evaporator temperature by resetting the chilled water set point warmer. There is a relatively small impact on lift when load is reduced because the delta T through the condenser is lower at part load. In many cases, chilled water temperature is constant. Therefore, reducing condenser water temperature is used to reduce lift. Understanding the differences between load and lift is critical to ensure the benefits of drive technology are attainable and balance the higher first cost with potential energy savings. Centrifugal compressors are variable volume. Therefore, either inlet guide vanes alone or the combination of inlet guide vanes and a variable speed drive will respond to a change in load and result in reduced power consumption. All types of chillers benefit from lower condensing temperatures. Variable speed drives simply allow more benefit by improving the part lift efficiency of chillers. As Bonnie's going to discuss, a variable speed drive is a very common chiller retrofit. Why wouldn't it necessarily be the right option when replacing a chiller? In a retrofit using the existing chiller, a VSD is likely to improve the performance more than any other upgrade, especially if controls are also upgraded at that time. But when we're replacing a chiller with a VSD is just one option. We ought to consider investing in a constant speed chiller at the same price with a higher full load efficiency. In either case, make sure the new chiller meets both the full and part load requirements of 90.1. Then use a fully featured analysis tool to determine which has a better return on investment. After all, there are ongoing differences in maintenance costs between fixed and variable speed chillers. Here's an example performance for some equal price chillers, one with and the other without a variable speed drive. The fixed speed chiller has better full load performance, but its IPLV is not quite as good. So which would most benefit a building owner? Let's look at an example, then give some general guidance. The chiller we were replacing was 700 tons. Based on our review of the building loads in the present configuration and expected future use, we right-sized the chiller capacity from 700 to 600 tons. Now here's the performance of two same price chillers, one with a drive and one without. If this graph looks unfamiliar to you, note that the axis is kW, not kW per ton. You actually pay for kW, not for kW per ton. Some observations. At condenser water temperatures near design, the constant speed chiller is more efficient, the area shown here in yellow. At low condenser water temperature, or low lift, the variable speed chiller is more efficient, the area shown here in blue. So which makes more sense? Again, we need to perform an analysis that accounts for all of the loads. As the rating standard states, IPLV is not to be used as a surrogate for energy analysis. Consider the high-efficiency chiller when you have significant demand charges or in humid climates. In addition, if there are multiple chillers in the plant, the new chiller may never operate at less than 50% load, and it may operate at high load conditions quite often. If there is an air side economizer on the building, the chiller may be off during hours that a VSD would benefit. If there are many hours at low condenser water temperatures, consider a drive, but perhaps the best economics are to only put it on one chiller. Another issue that should be considered is the life cycle cost of the drive. A high-efficiency chiller uses more copper to increase heat exchanger effectiveness. In a properly maintained system, copper is very reliable and will last the life of the chiller. A variable speed drive will likely need significant investment, either a rebuild or replacement around once per decade. This cost must be accounted for in the life cycle assessment. Bonnie, what about upgrading an existing chiller?
Well, certainly one of the most popular retrofit options is adding a variable speed drive to an existing chiller. So we'll look at that first and then discuss a few other areas. Well, since this is a retrofit application, we comply with the efficiency requirements of 90.1 by ensuring that the modification reduces annual energy consumption. Just like the new chiller equipped with a drive, we need to make sure that the operating conditions are such that applying it will save energy. Then we need to look at what other factors, like controls, need to be considered when completing the evaluation. And following that, you'll want to perform an economic analysis to determine if the payback meets your organization's criteria. When a drive is added to a chiller, there's an inefficiency added. If the chiller operates at design load, chilled, and condenser water temperatures, then this would result in a 2 to 4% increase in demand. So you would not normally put a drive on a chiller that operates at design conditions the majority of the time. Since the benefit of a variable speed drive occurs primarily when lower condenser water temperature are available, we need to validate these conditions will exist enough hours of the year to provide a desirable return on investment. As Susanna pointed out, over the life of a building, it is not uncommon for a chiller to become improperly sized due to duty changes. The VSD can correct for this, providing the right tonnage at the lowest energy cost. The first thing to note is that at design conditions, kW rises. That's that 2 to 4% inefficiency of the drive that we pointed out before. Similar to the previous examples, let's look at a 700-ton chiller operating at a 600-ton load. Now next note that if the condenser entering water temperature is held constant, there's no benefit from adding a drive. So in a very humid climate, such as Singapore, Puerto Rico, Miami, or Houston, there may be no benefit in applying a variable speed drive to an existing chiller, since there's little to no lift reduction available. However, there are kW savings available when the condenser water temperature, that is the lift, is reduced. As you can see here, operating at reduced load and lift provides substantial savings, on the magnitude of 35% when operating at 600 tons. Now let's look at a couple other considerations. So what issues should we consider when examining the economics of retrofitting with a drive? First, as far as the utility rates are concerned, ask, will the increased demand cost very much? Be sure to determine how large the demand charge is and if there is a ratchet that applies that demand to all months. If there is, it may be possible to limit the maximum demand through the unit controls. Now next, are there enough hours when the lift is reduced and operating conditions are advantageous for the drive use? If the system is equipped with an economizer, the available hours that would be used for calculating the drive savings will normally be decreased. We also need to remember that lower cooling water temperature is not free. Additional tower fan energy is necessary to produce that lower tower water temperature and should be accounted for. Another option would be applying a VSD to the fan tower motor. We'll touch on that later. Finally, if the chiller is oversized for the load, this load reduction in tandem with the lower condenser water temperatures may offer significant savings. As Susanna pointed out earlier, removing false loads and accounting for building improvements should not be overlooked. Upgrading your existing chiller to improve energy efficiency, while a noble cause, still needs to make financial sense for your organization. You must consider the first cost, which are often reduced by incentives, to the predicted energy savings to determine your return on investment. Life cycle costs should not be overlooked either. The return on investment must meet your organization's internal requirements and goals. Now I want to point out that there are many government and utility incentives out there ranging from rebates to low to no interest loans. These vary greatly by state and utility. As energy demand increases, utilities are being very creative in helping businesses find ways to finance energy efficiency improvement projects and reduce energy consumption. Savings of 10 to 30 cents per kW is common. Rebates for VSDs are often tied to the drive horsepower. For example, $80 per horsepower in California. These can significantly reduce the payback period. Now there's a great resource at DSIRE, the database for state incentives for renewable and efficiency. This is a project of the North Carolina Solar Center and the Interstate Renewable Energy Council, and it's funded by the US DOE. So what type of analysis should be performed in determining the potential energy savings? I'm a firm believer that bin analysis is not valid since load and condenser water temperatures are not coupled. The tools should simultaneously account for actual load and weather, operating hours, number of chillers, economizer capabilities, pump and tower use, and the actual utility rate. There are tools available that allow such analysis to be performed in 30 to 45 minutes. Trane offers several tools that account for these factors and provide easy plant configuration comparisons. Now, there's a few other modifications worth mentioning. If you're already budgeting a chiller overhaul, consider what changes you can make to it to increase efficiency. You might trim or replace the impellers on a centrifugal, or add ice making to your screw chiller to take advantage of the chiller capacity available at night. For water-cooled chillers, using your eddy current testing results, if many tubes are plugged or need to be plugged, retubing to a more efficient design may make sense. Anything you can do to return the chiller to like new or better efficiency for your current operating load should be evaluated. Since the labor content of overhaul is usually a significant portion of the cost, this is the ideal time to make these changes. So for example, at a data center in the Pacific Northwest, they systematically overhauled all their screw chillers and are saving 4% on their chiller energy cost. These savings have been verified by the local utility company. In summary, there are a variety of chiller upgrade opportunities that should be evaluated as part of your study. Take advantage of maintenance activities when you're making these changes when you're already applying the labor. Be sure to compare the first and life cycle cost to the projected energy savings to determine the return on investment. In many cases, you may be able to combine upgrades for an even better payback. Knowing the original design conditions and building load and where you're taking your building will be the key to making the right decisions. Now let's look at a few system retrofit ideas before we go through more extensive system changes. One method for reducing energy consumption is to add free cooling. This may be through the addition of a heat exchanger, a plate and frame water side economizer, or by modifying the centrifugal chiller to add refrigerant migration free cooling. For this to provide savings, the ambient wet bulb temperature must be low enough. When this is available, the heat exchanger transfers heat from the returned chilled water to the water returning from the cooling tower. This can either be used instead of operating a chiller or to pre-cool the water to an operating chiller. Both methods will reduce energy use. Similarly, a dry cooler may be used in an air-cooled chiller system to provide free cooling. Susanna, do you have any other ideas for air-cooled systems?
Sure do. What about adding ice? In many cases, you may already have glycol in the chiller for freeze protection during colder seasons. And even if you don't, many air-cooled chillers are still capable of building ice. It just has to be enabled. In other situations, you may be doing a chiller refresh, and any necessary controls or compressor upgrades would be performed at that time. Now, the beauty of this option is that it takes an existing system, pipes, coils, air handlers, etc., and reuses them in a way that saves energy and/or energy cost without a lot of added expense. Other benefits include: 1, lower run times on equipment. You likely won't need all of the chillers to charge the tanks many days of the year. And 2, chiller maintenance during normal business hours, even in the summer. Depending on the hours when tanks will be charged, you may want to consider some acoustic attenuation modifications. Consider the neighborhood. Chillers making ice tend to be louder than they normally would have been, and this change in acoustic signature is a lot more obvious when it's quiet at night and in the early morning. Is this application in a residential neighborhood? Is it on a lower roof with taller buildings adjacent? Many times of the year, ice production can be completed in the early evening hours, or the ice charge can last more than one day. Acoustic attenuation could be on the chiller itself, or an acoustic barrier such as a wall between the chiller and the neighbors. But be mindful about where you put any new walls. Too close, and it may cause too much recirculation of condenser air. So why is this a more attractive option for an existing air-cooled chiller and not water-cooled? Here's a popular graphic from a past broadcast. Air-cooled shows a better efficiency benefit from ice storage. This is because during nighttime ice-making mode, the ambient dry bulb drops more significantly than the ambient wet bulb. This graph shows the difference between design ambient temperatures, both dry bulb and wet bulb, for a day in August. Note that the ambient relief for dry bulb is always more than the ambient relief for wet bulb. This difference in condenser relief is key to understanding that air-cooled ice systems perform efficiently during the ice build mode. An air-cooled chiller can make ice at night with better efficiency than that same air-cooled chiller makes chilled water during a design day. This slide shows that an air-cooled chiller in ice-making mode still has a slightly higher energy efficiency ratio than the same chiller on a design day making 45 or even 50-degree solution. This is due to the condenser ambient relief from 95-degree daytime temperatures to 75-degree nighttime temperatures when ice is being made. But just like with the kW per ton versus kW, the EER doesn't tell the whole story because the size of the chiller needed in an ice storage system affects the full load kW, and in the case of partial storage, there are more run hours on the ice storage chiller. We have to go to kW to find out what will be setting our on-peak demand charge and to kilowatt hours to compare actual energy use. Now, another reason why ice is a great system modification for air-cooled systems is because these systems are often smaller, making it simpler to add ice in an easily controllable way. Because air-cooled is likely a positive displacement chiller, we put the storage tanks downstream of the chiller. The chiller receives the warmest entering fluid temperature and produces a higher leaving fluid temperature than it would if the chillers were downstream. The downstream tank location increases efficiency and capacity for positive displacement chillers. This example shows an air-cooled chiller with ice downstream and one pump. The system is quite simple, but it has limitations. Night cooling loads while the tanks are being charged will have to use the cold charge mode chilled fluid temperatures. If the pipes are already insulated, this shouldn't be a problem. What might be a problem is that the window for building ice narrows when there are nighttime cooling loads. Proper examination of the current chiller operation can tell you what your loads are when you want to be making ice. But there's another benefit of an ice retrofit that is just as attractive for water-cooled systems as it is for air-cooled, and that is right-sizing using ice. Now, we normally show this graph when discussing full versus partial storage, but it also illustrates your oversized or undersized existing chiller versus the current or desired system's design day load profile. If your building has too big of a chiller today, you may be able to completely avoid the on-peak window, since you can make a lot of ice at night if you get enough tanks. Since the oversized chiller is a sunk cost, a few more tanks, especially where rebates or other incentives are available, can be a real game changer when considering full storage. Or simply use the added capacity of the oversized chiller to shed more of the expensive electricity, whether on-peak or demand-related charges. Conversely, if your building has too small of a chiller, instead of adding more chillers, ice can be your system expansion. Here we have a fully utilized chiller doing all it can on the design day, and ice made when the loads are reduced makes up the difference. You may recall we discussed ice storage design and control in a 2009 broadcast. Chiller capacity reduction due to glycol must be considered when defining the operating modes. Another key point on existing systems is eliminating the glycol penalty on existing cooling coil performance. Reducing the supplied fluid temperature restores full coil capacity without increasing pumping or fan energy costs. An extra slide included in your handouts shows the reselected existing cooling coils. So that's it for the overview on adding ice to a positive displacement chiller system. Mick, what other system retrofit options are there?
Well, there are a bunch of them, and we're going to stay outside the flanges of the chiller as we begin examining those system options. Okay, a pop quiz. What's the design delta T on most chilled water systems? How about the condenser water flow rate, and why? In the past, many chillers were selected and systems were designed using these AHRI standard test conditions. There are a lot of chillers that were selected to make 44-degree chilled water with a 10-degree delta T, and with a condenser water flow rate of 3 gallons per minute per ton, entering at 85 degrees. In the past, this was also a 10-degree delta T, but with today's more efficient chillers, it's closer to about 9.5 degrees. Yet today, the ASHRAE Green Guide recommends expanding the chilled and condenser water temperature differences and reducing the respective flow rates. For example, on the chilled water side, the Green Guide suggests a 12 to 20 degree delta T and condenser water delta T of 12 to 18 degrees. Kelly and Chan, who were consulting engineers in Boston, performed a study and wrote a paper that recommends similar numbers. Now, what prompts their and the ASHRAE recommendations? Well, we often think of kW per ton for a chiller. Another measure of chiller efficiency is COP, or coefficient of performance. We can calculate it by dividing 3.516 by the kW per ton. For COP, higher is more efficient. Now this chart summarizes the dramatic improvements in chiller efficiency during the last 3 decades. It shows the minimum requirements per ASHRAE standard 90 between 1977 and 2010, as well as the best efficiency we could find today. So in 35 years, the minimum required efficiency of centrifugal and screw chillers has increased more than 60%, and smaller scrolls and recips by over 40%. That's huge, and that's not even the best chillers. In that same time frame, both condenser water pumps and cooling towers have seen very minor efficiency increases, mostly motor improvements. That's why those involved at ASHRAE and Kelly and Shan investigated and found that reducing flow rates and having the chillers working a little harder is a good idea. Chillers are extremely efficient. Now, some claim that reducing flow rates and expanding temperature differences is only for new systems. As we'll see, the concept also works very well in system retrofits. Now, unless otherwise mentioned, in the examples we're going to share, we'll be assuming that the coils have two-way valves. First, let's look at how this affects the chilled water side of the system. The amount of heat transferred from a cooling coil is dependent on the equation U times A times LMTD. As Don Appelheimer used to say, everyone remembers what LMTD stands for, lovely, magical temperature device. That's what a coil is. And its log mean temperature difference is an asset that can be exploited. In an existing application, the coil area is constant. By changing the entering water temperature, the valve controller modulates, as does the water flow rate. The result is that the same amount of heat is transferred across the coil. Said another way, to satisfy the same load, if we put less water at a colder temperature into the coil, it will come out warmer than it would have. Let's look at an example. This coil was originally selected to deliver 504 MBH or 42 tons. The entering water temperature is 44 and 101 GPM is required. Now note, this is the old high flow rate of 2.4 GPM per ton. The water leaves the coil at 54 degrees, giving a water temperature rise of 10 degrees. Now in this example, we want the same airside performance from the coil. Since the airflow and the entering and leaving air conditions are the same, this coil must still produce the same MBH, 504. But what if we send the coil colder, 41-degree water? In response, the coil valve modulates to allow less of that cold water, reducing the flow rate to 63 GPM. Note that the reduction to 1.5 GPM per ton is in line with the ASHRAE Green Guide recommendations. This results in an increase in leaving water temperature to 57 degrees, giving a 16-degree water temperature rise. This means the GPM has been reduced by over 37% because we've reduced the supply water temperature to the existing coil. Now we'll use this concept in just a minute, but first, let's look conceptually at how reducing flow can help. The pump laws tell us that pump kW decreases with the cube of the flow rate. We need to remember that that's for free discharge systems. In real life, we don't quite achieve the cubic savings. But even if we use the 2.5 power rather than the cubic, the pump power reduction is over 70%. While the chiller uses a little more energy to make colder water, this is usually more than offset by pump energy savings. There are also other possible advantages for system expansion made available by reducing the chilled water supply temperature to existing coils. Let's say that an addition is planned and we want to use the existing chilled water pipes and pumps. By reducing the flow to the existing portion of the building, the rest of the flow can be used by the addition. We'll see in this next example how this concept allows project teams to increase capacity of their pumps and pipes by more than 50%. And this isn't just theoretical. It worked very well in a healthcare facility in Opelika, Alabama, as well as other projects. They had an existing hospital and clinic that had been added to over the years. It was time for another addition, but this time it was a big one. They needed to expand the facility from 2,000 to 3,000 tons. The existing coils at design conditions used 4,800 GPM, 44-degree chilled water, and a 10-degree temperature difference. To reduce the flow rate through the existing coils, we selected new chillers making 40-degree chilled water. This resulted in a 16-degree delta T at the air handlers. Now note that this 40-degree water temperature is a degree lower than our original example. That shows that it's important to reselect the existing coils to determine their performance, rather than using a rule of thumb. Now, use of the colder water reduced their existing coil flow requirements by 40% to 2,880 GPM. The rest of that water, over 1,900 GPM, was pumped to the new addition. And they were able to use the existing pipes and pumps just by selecting the new, higher capacity chillers at the proper conditions. As we worked on the job, there were a couple of things that we had to watch out for. The first was pipe insulation. Originally, we had hoped to be able to reduce flow rates even more by selecting the new chillers with a 38-degree chilled water temperature and expanding the delta T to 20 degrees. However, the facility manager looked at their existing pipe insulation and determined that if the chilled water temperature were below 40, that they might experience unwanted condensation. The second issue was that some of the existing control valves were oversized. At the reduced flow rates, they would have been even more oversized, and the control would get worse, especially during part load conditions. So, they changed the valves out on the largest existing coils to get the biggest bang for the buck from a labor cost standpoint. Now I was back at the facility after all the changes were made, and everyone loves the system. So using lower chilled water temperature in the existing chilled water system is ideal for system expansion. But there's another option for using cold chilled water temperature we haven't discussed yet. Let's say there's an existing space, such as an operating room, where the space requirements have changed and they need to satisfy more load. By sending the existing coils the same amount of colder water, more load can be satisfied in the existing space. Simply reselect the coil with the same flow rate, but at a lower entering water temperature. You'll see the effect on leaving air conditions and an increase in coil capacity. Now, let's look at retrofit possibilities on the condenser water side. We get to speak with building owners and engineers quite often. About every 2 weeks when we share our next example, the engineer will turn to the owner or vice versa and say, "That's exactly our system." Here's the situation. It's time to replace the chiller, but the cooling load has increased. The cooling tower had rotted out 2 years ago and was replaced, so it's in good shape, as are the new condenser pipes. The condenser piping goes under the parking lot, and nobody wants to rip up that parking lot again. This situation probably sounds familiar to at least one person in the room. Often the first thought is that the entire system needs to be replaced, and the job goes out of budget. There are alternatives. Here's an example with an existing helical rotary chiller of just over 150 tons with 450 GPM of condenser flow. The tower was originally selected at 78-degree wet bulb and 85-degree entering condenser water temperature, which results in just under 95 going back to the tower. It met the ASHRAE 90.1 requirements when it was selected 20 years ago. The chiller needs to be replaced, but the building requires more capacity. So we want to increase the capacity when we purchase a new chiller, but use the same condenser water pump, pipes, and cooling tower. If we reselect the tower at different conditions, we find that it can easily reject the additional heat from a higher capacity chiller. Combining tower and chiller selections, we can see that we can select a chiller that can either produce 38% more tonnage, or we could select an even larger chiller that would give us up to 51% capacity increase. But there's no free lunch. First, at each step, the chiller is physically larger. Next, you notice that the cooling tower can reject the heat, but the result is higher condenser entering and leaving water temperatures. However, since the chillers are newer, they're more efficient than the 20-year-old chiller, even at the raised condenser conditions. Using the existing pipes, pump, and cooling tower may well bring the job back into budget and allow it to move forward. But the owner pays for the entire system to operate, so let's look at how this affects system power. The existing cooling tower fan used 5.9 kW, and the condenser water pump used 8.6, with the chiller using 128 kW. When a larger chiller is installed, there are more tubes in the chiller's condenser, and the condenser water pressure drop goes down. This means that the pump kW can be reduced, most likely by throttling its flow using a variable speed drive. We'll talk about that more in a few minutes. But make no mistake, as the capacity rises, so does the demand and the energy the system will use. But due to the new, more efficient chiller, the system is still more efficient from a kW per ton perspective than when it had a 20-year-old chiller. Before we move on, let's look at one more thing. What if our electrical capacity was limited? How much more cooling could we install for 128 kW of chiller power? Almost 30 tons, or an 18% increase. So there are a lot of options to use the existing condenser side infrastructure.
The bottom line is to not be handcuffed by the past system design. There are many ways to maximize use of the existing infrastructure, pipes, pumps, and cooling towers and coils. Treat them as assets and have some fun satisfying customers' retrofit needs. In addition to chiller changes and design parameters, there may be times when changing the system configuration provides significant benefits. Many of the newer chiller controls allow variable evaporator flow. Let's examine the opportunity, discuss requirements, and look at ways that this can be used. We've covered variable primary flow systems in several E&Ls in the past. Here are 3 system issues that we've discussed before. First, remember to keep the flow rate between the minimum and maximum flow rates allowed by the chiller manufacturer for the installed chiller. Next, make sure the minimum flow rate can always be maintained. And third, make sure that the flow rate changes are within those allowed by the chiller unit control. Bonnie will address this more in a few minutes. If people haven't used systems that allow variable chiller evaporator flow rates in the past, why are they being considered today? Now, first and foremost, in the past, manufacturers told you to maintain constant flow through the chiller's evaporator. Today, sophisticated feed-forward control allows the chiller to react quickly to changing conditions. Therefore, some new chiller controls accommodate varying evaporator water flow rates. Retrofit opportunities are primarily to reduce pump energy use or to respond to system issues, such as the so-called low delta T syndrome. Low delta T occurs when coils selected to provide a specific temperature difference return water at a lower delta T. This could occur because the coils are dirty, airflow is not correct, controls are being performed improperly, or even because the coils have 3-way valves. Mick, why don't you walk us through several retrofit scenarios?
Will do. We'll start small and move up. In a small single chiller system, if the chiller controls allow variable flow, a retrofit from a constant to variable flow system may be simple. First, determine the chiller's minimum flow requirements. Next, find 3-way valves that, when their flow is summed, allow the chiller minimum flow rate to be met. It would be best if they were hydronically the furthest from the pump. Put a differential pressure sensor at the most remote air handler that has a 3-way valve. Now, to make the system variable flow, convert the rest of the 3-way valves to 2-way valves. Finally, put a drive on the pump and control it to maintain the system differential pressure set point. A drawback is that there will always be more water being pumped than necessary, so pumping energy will be a little bit higher. But if the minimum flow rate is low, the additional pumping power will be minimal. This can work extremely well in single chiller applications because of its simplicity. Chilled water system savings for a 2-story office building in St. Louis were shown to be about 6% annually. Now, how about larger constant flow systems? Simply put, this is low-hanging fruit from an energy standpoint. There's a lot of money being spent to pump water through the system. Follow the same steps as for the smaller system. Determine the minimum flow rate. Find enough 3-way valves to allow it. Put a DP sensor at the most remote 3-way valves. Convert remaining valves to 2-way, and add VFDs to all pumps and control them to maintain the DP set point. But we now need a system controller to sequence chillers on and off, as well as to ramp the pumps up and down as the chillers sequence. When the system is larger, the opportunity for savings is also larger, but so is the investment, both in terms of work and cost. So, what has to happen to convert a system from primary-secondary to variable primary flow? Jeannie let me develop my own graphics for this one. First, the primary pumps must all be removed from the system. Next, the distribution pumps must be moved so that they're now on the chiller side of the bypass line. They may also need to be increased in size since they must now overcome the pressure drop through the evaporator bundles. The bypass line is also way too big, so it needs to be downsized for the largest chiller's minimum flow rate, and we need a control valve. In addition, we need to add a way to monitor chiller flow rate, either a flow meter or DP equated to flow rate for each chiller. That's a lot to do and basically requires reconstruction of the system. So, does anybody retrofit from primary-secondary to VPF? Sure. With all the changes, why? It could allow the system to respond to low delta T syndrome. It doesn't fix the low delta T, that needs to be done at the air handlers, but the chillers can be overpumped and given more than their design flow without exceeding their maximum flow. This allows them to load more fully. If the entire plant is being changed, you will end up with a true variable primary flow system, and it frees up a lot of space in the room. After Brenda Bradley and I published an article on VPF more than 10 years ago, we received the following response in a letter to the editor. Simply put, the VPF system ends up with a lot less space needed for pumps. In this case, allowing an additional 1,000-ton chiller to be installed in the space that used to be occupied by all those primary pumps. I was once told after an entire system reconstruction that they had, quote, a mountain full of pumps to discard after totally converting their system. With that said, many times a full chilled water system replacement is either untenable or way out of budget. What's another alternative? How about converting from primary-secondary to variable primary, variable secondary? Fewer changes need to be made, and they're much less invasive. For our example, we're going to start with primary pumps that are manifolded. First, add a VSD to the primary pumps, and while you're at it, open the balancing portion of the triple duty valve wide open and use the VSD to balance the flow rate and set the maximum pump speed. You'll likely save energy just by doing that. Next, if they aren't there already, install temperature sensors in the return line from the system and to the chiller. Control the pump VSDs so that the return temperature to the chillers is a degree or two lower than from the system. This ensures a little excess flow in the bypass line all the time, but more importantly, that the system chilled water set point is always maintained. Finally, install flow sensing devices such as DP sensors at each chiller to ensure minimum flow rate. If the temperature control of the pump VSD results in flow approaching the chiller's minimum, this sensor will speed up the drives on the pumps. So, There are a number of options to convert to VPF. But Bonnie, the chiller unit control has to be able to react to the evaporator flow rate changes. Can you tell us a little bit about what has to happen from a unit control standpoint?
Sure can, Mick. Just think of your PC. You would not try to run today's applications on a computer that is 10 years old, because even if you could get it to work, you would not have the technical support and parts available. Well, neither should you count on your existing unit controls to be adequate to provide the precision and reaction times needed to optimize your upgrade investments. You want your controls to be able to communicate with your BAS and provide the sequencing necessary. So keep in mind that it may be necessary to include this controls upgrade in your analysis. Typically, older systems do not have the unit controls necessary to react to the evaporator flow variation. To illustrate this old control deficiency, let's look at a rapidly changing flow situation. Here's our layout after converting to a variable primary flow 2-chiller system. Transitioning from 1 chiller operating to 2 chillers is the hardest. The first chiller is operating and at some point becomes fully loaded and can no longer meet the temperature requirements. At that time, the isolation valve on chiller 2 is opened. If it opens quickly enough, the flow rate through the operating chiller drops by 50% very rapidly. Let's see how the controls react in this situation, which is a very rapid flow rate change. Okay, so here we show what will happen to a chiller with a 15 to 20-year-old unit controller when we change the flow. This is similar to the disturbance you might see when another chiller comes online, like I just described. In this example, we have decreased the flow by 50% over 30 seconds. When we reduce the flow, the chiller becomes unstable, hunting for the set point with the change in flow. With the instability, the chiller reaches its differential to stop and the chiller cycles off. As the chiller is restarting, the temperature of the chilled water loop continues to increase, and when the chiller does come back on, it has to pull the temperature gradually back down to set point. So why is the chiller unstable? Because the design delta T is set at full flow. For example, a 10-degree delta T at full flow would be 20-degree delta T at half flow. And if the adjustment for the inlet guide vanes is set to full flow, the adjustment would be too coarse for the part flow. Too coarse means overcompensating and spinning out of control, as you see in the graph. For this reason, you might have set the delta T at half flow condition. What this would do is make the adjustment too fine at full flow, making the chiller react to change much slower. The chiller would stay online, but would not react as fast. So what are the characteristics of modern controls? Let's discuss what they're capable of. Historically, controllers using feedback-only control wait until the temperature is affected before making a change. Modern feed-forward controls react before the temperature is affected. We'll take a look at this in the next slide. So building upon this, compensating controls use algorithms to auto-adjust and provide the most effective control, since they easily overcome the variations that will result from normal operations and significant flow changes. If we compare a compensated feed-forward control to the previous system, you can see how much more stable the leaving water temperature is, even with a dramatic reduction in flow in a short period. Not only did the chiller stay online, but its chilled water temperature changed very little. This is the type of control now available for use in variable primary flow systems. As you can see, having a controller that is capable of reacting to rapid changes in flow will provide efficient operation and significantly better temperature control in your system. Another control upgrade benefit is the coordination of work between the inlet guide vane and the variable speed drive. Simultaneous optimization of speed and capacity control is important when trying to get the chiller's sweet spot quickly in order to save energy. This feature of the latest generation of controls is particularly important when flow is changing at the same time. Having a controller that is retuned for the present flow rate makes variable flow and variable impeller speed possible at the same time. Without upgraded controls with flow compensation, you may not save very much energy with the VSD in a variable flow setting. Consult with the chiller manufacturer to find out how suitable your existing chiller and chiller controls are for variable flow. Susanna, what about system level controls upgrades?
For control retrofits, there are 5 topics we'll discuss today. The first one is pump pressure optimization, a new requirement of 90.1. Next is a question we get asked a lot: how many chillers should be operated? Then, how should the cooling tower be controlled to minimize chiller plus tower energy? We'll then go into the number of tower cells to operate and end our program today with a hot topic: variable condenser water flow. Okay, so the first one is pump control. A common strategy is to operate the pump to supply a constant system pressure differential at the most remote air handler. If all valves in the system are partially closed, the pump speed and pressure set point are too high. Here's a better way. It's a cascaded control loop. That is, we have a pump speed determined by providing a specific pressure leaving the pump. This control is active all the time. Every 15 minutes or so, the automation system has the option to reset the pressure set point based on valve position. The valve position doesn't directly adjust the pump speed. It gradually has an influence on it by resetting the pump pressure set point. Referred to as pump pressure optimization or critical valve reset, this reduces system pumping power substantially. The same concept has been used on the air side for over 2 decades. With the advent of direct digital control of valves, pump pressure optimization is being used more often than in the past. Let's look at how it operates. The DDC controllers indicate the position of their individual control valves. The building automation system continually pulls the DDC valves at the coils, looking for the most open valve. It then resets the pump static pressure set point so that at least one valve is nearly wide open. As a result, the pump generates only enough pressure to obtain the required flow through the critical terminal unit. This graphic shows the simple control logic. If the worst case valve is between 65 and 75% open, we're already operating efficiently. If the system controller senses that all valves in the system are less than 65% open, it lowers the pump speed set point to reduce the water pressure. The valves will respond by opening to maintain the same water flow. If any valve is 75% open or more, the pump pressure set point is too low, and the control system will adjust the speed to increase the static pressure. In addition to the obvious pump energy savings, this method assures that zones aren't starved for water. This control is required by ASHRAE 90.1-2010 in many systems with direct digital control valves. As I said in the beginning, watch for rogue zones so that they don't defeat this control. On to the next topic. It's a question that seems to come up quite often today. Should I operate 1 chiller at nearly full load or 2 at part load conditions? To begin the discussion, we'll only look at chiller performance. We'll then expand it to include ancillary energy. Many in the industry receive chiller performance from manufacturers who rate the chiller in accordance with AHRI 55590. In the standard, a term integrated part load value is defined and data is provided to allow calculation of the IPLV. Looking closer and combining representative chiller performance values with the 4 chosen conditions for IPLV highlights another controversial industry issue. That is, the recent claims that running 2 chillers with variable speed drives at part load is more efficient than 1 chiller fulfilling the same load. Of course, if attention is focused on these numbers, the assertion seems authentic. Here, the 50% load value of 0.308 kW per ton has a commanding efficiency advantage over the full load value of 0.572. But the 50% load number has condenser water that is 20 degrees colder than the full load number. Of course it looks more efficient. Its lift has been reduced, especially since, as we discussed earlier, variable speed drive chillers are part lift devices. We need to compare those chillers at the same condenser water temperature. So let's do that. The results for a system of 90% load and with the condenser water temperature shown are represented here on the table and include only the chiller kW. Unmistakably, until the tower water temperature falls below 70 degrees, 1 variable speed chiller operating at 90% load consumes less power than 2 equally loaded variable speed chillers. It's worth emphasizing that this comparison does what IPLV cannot: compare like chillers in a like condition, apples to apples, if you will. In addition, this is only chiller energy used. Remember, these cold tower water temperature conditions may not be economically attained. Also, pump and tower energy were not included in the previous slide. Assuming a VPF system on the chilled water side, but constant speed condenser water pumps until the tower temperature goes below 65 degrees, only 1 chiller should operate. But that's only one load point. Let's expand this and look at comparisons in different loads and different tower temperatures. This graphic compares 2 versus 1 chiller operation at building loads from 50% to 90%. Operating 2 chillers would put half that load on each chiller. The only time when operating more chillers is beneficial is when the tower temperature is below 65 degrees and the load on a single chiller is 90%. At all other conditions, operating fewer chillers is beneficial. So, if you want to operate more chillers than needed, don't do it until the tower leaving water temperature is below 65 degrees and plant load is 45% or less, or if the plant load is below 40% and the tower water is less than 60 degrees, and regardless of tower water temperature, turn a chiller off once the plant load is 35% or lower. I think you'll find very few hours when an extra chiller could be operated without wasting energy. Mick, I think it's time to dive further into coordinating chiller and tower control for reducing system energy.
You bet. Many times it can be beneficial to retrofit a variable speed drive to a constant speed cooling tower fan, or the tower might already have one. The question then is how to optimize control to reduce the system energy consumption. Now, this isn't exactly new information. Beginning in the early 1990s, various methods were developed to find that optimal set point at each operating condition during the year, and the results are similar. The list here represents 3 control providers, 3 different chiller manufacturers, a large utility, and a cooling tower manufacturer. Let's look at an example of the concept, then discuss savings available. Here we have a chiller operating at 60% load when the outdoor air wet bulb temperature is 65 degrees. If the tower fans are operating at full speed, 73-degree water can be provided. If at half speed, 79 degrees. The chiller power rises at the elevated condenser water temperature. But what the chiller system owner pays for is the sum of chiller plus tower energy use. And the goal is to find the tower set point at which the sum of the chiller plus tower energy is minimized at each point in time. For a given chiller plant, it's a function of chiller load and outdoor air wet bulb. So, how is this optimal temperature calculated? For a given chiller plant, we first define what are the design parameters of the cooling tower. Also, the chiller design parameters and the chiller type. Optimal control changes depending on the chiller type because each chiller reacts differently to the condenser temperature relief or lift. At each point in time, we can calculate the optimal temperature by looking at the chiller load, often done using temperature difference divided by the design temperature difference, and the ambient wet bulb temperature. So, what kind of savings are available? In their ASHRAE Journal article, Hugh Crowther and Jim Furlong estimated savings from 2.6 to almost 8.5% by finding the optimal tower temperature. And in our E&L on cooling towers, we showed savings up to 14%, depending on location, in this case for a hotel. Specific project estimates of savings can be made in half an hour by using software such as Chiller Plant Analyzer. Okay, let's go further now. If there are multiple chillers and multiple cooling tower cells, how many cooling tower cells should we operate when we have fewer chillers running? From a high-level standpoint, the answer is as many as possible. The reason is that cooling tower cells are heat exchangers. Since the expenditures have already been made, when possible, use more heat exchanger surface. The larger the heat exchanger surface, the better the heat transfer. The better the heat transfer, the closer the tower leaving temperature approaches the outdoor air wet bulb. The closer the approach temperature, the lower the airflow needed to make the water cold. And finally, the lower the airflow, the lower the tower fan power. Let's look at an example of operating more cooling tower cells. Here, we have 2 500-ton chillers selected at design conditions, each with a 1,000 GPM condenser water pump. A cooling tower is selected, and it has 2 cells, each with a 40 horsepower fan. At this point in time, there's a 200-ton load and one chiller is operating. This results in a 5.6 degree condenser water delta T. For this discussion, we set the condenser water flow at design flow of 1000 GPM for the single chiller. Cooling tower performance is shown here. The first column is the operation with a single cell. To achieve the 65-degree set point, at this point in time, a single fan needs to operate at full speed, and that consumes 40 horsepower. If the same water flow is sent over 2 cells, there's more heat exchange surface available. To achieve the same tower set point, the tower fans can be slowed to 39% of their design speed. And combined, they use 16.6 less horsepower than operating the single cell. But remember that the water flow over each cell must stay above the minimum flow rate required by the tower provider. What happens if the flow rate drops too much? As the water flow drops, there comes a point that the tower design does not distribute the water evenly throughout the fill. This can lead to dry spots in the cooling tower. Since the pressure drop through the dry fill is lower than through the wet fill, more air will flow through that dry area and the heat transfer will be reduced. In addition, scale can form on areas of the tower fill experiencing reduced flow. This again leads to poor heat transfer and increased maintenance. In extreme conditions, icing can occur on cooling towers. I still remember the year the applications team was riding the train back from the ASHRAE meetings in Chicago, and Susanna pointed out through the observation deck windows the large block of ice that formerly was a cooling tower.
I remember that well. Those cooling towers were huge. There was like 30-foot tall ice falls hanging all the way around. Now I know a bunch of ice climbers would have just loved to get out there with their crampons and ice axes and have some fun. But surely there's a way to have a more constructive fun with variable flow in the cooling tower.
There sure is, Susanna. The final retrofit opportunity we'll discuss today is putting a variable speed drive on the condenser water pump. We discussed this in a 2006 E&L on variable speed drives, but this subject comes up a lot, so we wanted to address it specifically with respect to retrofits. First, you need to make sure that the pump motor is compatible with a variable speed drive. If not, you can't just slap a drive on it or you'll have issues. Most condenser water systems have triple duty valves that balance the system, delivering the condenser water flow at full pump speed. One great reason to add a VSD to the condenser water pump is so that the balancing portion of the valve can be fully opened, the pump speed ramped down to give the design flow, and pump energy can be saved without affecting anything else. That will likely pay back in many applications. The VSD can also be used for head pressure control. The next question is, should we vary the flow rate during system operation? There are possible savings, but because of all the changes, it's complicated and there's a minimum pump speed. Let's look at that first. One thing to note is that the minimum pump speed may be set by one of 3 limits. It may be at the minimum allowable flow rate through the chiller's condenser. The chiller minimum is required to maintain good heat transfer and chilled water temperature control. The second isn't normally experienced but should be checked. Enough pressure must be developed to lift the water from the cooling tower sump to the top of the cooling tower, the open portion of the loop. If we reduce the condenser water pump speed too far, we'll get no flow over the tower. And we just discussed tower issues concerned if the flow is too low. Remember, there's always a minimum. With that preface, let's look at system operation when condenser flow is reduced. Cooling towers can reject heat at many conditions. Shown here is the performance of the cooling tower with a chiller load of 70% and an outdoor air wet bulb temperature of 70 degrees. We've charted the temperature of water entering the cooling tower. On the right side of the chart, we see that the water temperature entering the tower is about 84 degrees at 100% water flow. If we reduce the water flow rate, the temperature entering the tower goes up. Since we're rejecting essentially the same amount of heat with lower water flow, the water temperature entering the tower rises. For example, at 50% flow, it's 96 degrees. Now, since the tower entering water temperature is the same as the chiller leaving condenser water temperature, we can look at the chiller power at these same conditions. At the same chiller load, as the water temperature leaving its condenser rises, so does chiller kW. Now, if we just look at chiller kW, we'd never reduce the condenser water flow rate. But we need to add the cooling tower fan kW, the pump kW, and the chiller kW so we can see how the system operates. Remember, this is one snapshot in time, 70% load and 70-degree wet bulb. We'll look at a few others in a second. Here, we show results assuming the cooling tower fan speed is held constant at 100% to produce the coldest water possible coming back to the chiller. The minimum chiller plus condenser water pump plus cooling tower kW occurs between 80 and 90% of the condenser water flow rate. But it's not that easy. So far, we assume that the cooling tower fans are operating at full speed all the time. Because ASHRAE 90.1 requires speed control on cooling tower fans in many applications, and as we just discussed, there are significant savings by finding the correct tower set point, many people put VFDs on their cooling tower fans and want to use those VFDs. So, we need to examine how the condenser leaving water temperature changes when we decrease the flow rate and tower fan speed. Since slowing tower fan speed reduces airflow and heat rejection capability, the tower entering water temperature rises as shown on this chart. Since both water flow and airflow decline, the slope of the curves is steeper than before. So, let's look at all of these flow rates and tower fan speeds and see how the system kW compares. When we look at all the possible operating points, we see that the system kW is at its minimum when the fans and pumps are at about 80 to 90% of their speed. Reducing water flow rate further ends up using more energy in all cases. But this graphic also shows another important fact. While it won't occur with positive displacement scroll and helical rotary compressors, we have to be aware of it if we attempt this on systems with centrifugal compressors. Look at the top blue line, where the cooling tower fan is operated at 50% speed. Once the water flow rate drops below 80%, the temperature of water produced by the cooling tower rises so much that it sends the chiller's compressor into surge. If you're going to reduce flow rates and tower fan speeds, do so in a manner that keeps the chiller from surging. Okay, what we just looked at was the chiller operating at 70% load when the wet bulb is 70 degrees. That's one point in time. How about some others? What if the chiller is at 70% load, but the outdoor air wet bulb temperature is 50 degrees? This might occur in a multiple chiller plant when only one chiller is operating. Here, a tower fan speed of about 80% and a water flow rate of 80 to 90% is the best. Note that if the water flow gets turned down too far, the total system kW rises significantly. A piece of good news is that since the outdoor air wet bulb temperature is low enough, the chiller doesn't surge. Our final example examines the same system at 30% load and a wet bulb of 50 degrees. The system power consumption is fairly flat. One thing to note is that reducing the tower fan speed makes sense at all water flow rates. This reiterates what we saw earlier when we covered cooling tower control. Just because chillers can operate with colder entering condenser water temperatures does not mean it's optimal. Whether there is constant or variable condenser water flow, back off on tower fan speed and save some system energy consumption. Now the chart here shows the three operating points we just covered, but there are a lot more loads at various wet bulb temperatures. How do we control the system at all those conditions? In a job featured in the ASHRAE Journal in June of 2006, control of a chiller, pump VSD and cooling tower fan VSD was discussed. The control strategy at Winchester Medical Center is, until the chiller gets below 80% load, as measured by flow rate and temperature difference, operate the condenser water pump and tower fan at the design speed. This keeps the chiller out of surge and allows the system to operate efficiently. Below 80% chiller load, operate the pump and tower speeds to be 20% plus the chiller load. Once the pump reaches its minimum speed, maintain its drive at that speed and allow the cooling tower fan speed to continue to decline. On this job, the condenser pump minimum is 67% and is set by the need to produce the static lift from the basin to the top of the cooling tower. Presently, our suggestion is to look at the optimization of condenser water pump speed as an option to be examined for the particular job. Remember that the charts you saw today were for one specific application of a chiller, pump, and cooling tower. Depending on the efficiency and power draw of each, the results can vary significantly. Nevertheless, sometimes we're asked for guidance when people are considering variable condenser water flow. First, you need to determine whether or not reducing condenser water flow rates should even be considered. If you're already minimizing the condenser water pump kW, for example, by reducing its design flow rate to 1.5 or 2 GPM per ton, it may not even make sense to take the time to look further. Also, reducing just the tower fan speed may give you most of the energy savings, and it's simpler. If you do decide to reduce condenser water flow rates during operation, know the minimum condenser water flow rate for your system. Then, to find efficient operating points at various loads and ambient conditions, take the time to examine the system at all those loads and ambient wet bulb temperatures. What occurs in real life is quite different than what the AHRI chiller rating standard assumes. And remember that over the year, the number of chillers and cooling towers operating may also vary. One reason to study the system is to keep the chiller out of surge and thereby allow it to meet the cooling load. This is especially important at wet bulb temperatures closer to design. Once you've done this work, write a detailed sequence of operation. Finally, there's no replacement for being out at the job site with a system operator and seeing what happens during operation. Consider being part of the recommissioning team. The bottom line is that variable condenser water flow allows some system savings, but it takes more design examination and on-site fine-tuning to achieve those savings. We suggest that you first reduce condenser water pump power at design. You can easily do this by reducing the design flow rate. Then, determine if variable flow is still warranted. Jeannie, back to you.
Thanks, Mick. As we mentioned earlier, Mick authored an ASHRAE article covering some of the content discussed today. A bibliography with the article and additional resources for today's discussion is available. Ask for copies from your local site coordinator. And don't forget to check out the latest engineer's newsletter on single chiller central geothermal system design. Additionally, past broadcasts are available to order on Trane.com. So check the website for information on specific broadcasts or visit Trane.com/continuing education for on-demand programs accredited for LEED Continuing Education and AIA Continuing Education. Please remember to fill out a survey and let us know how we're doing. AIA members, please remember to turn in your information to your local site coordinator. Now we have 2 more E&Ls scheduled this year. Join us in June when we'll discuss design and control strategies that can significantly reduce energy use and ensure proper ventilation in VAV systems. And in fall, we'll cover various types of equipment used for dedicated outdoor air conditioning. So mark your calendars. Thanks for joining us today. We'll see you in a couple of months.